Okay, we are now starting Chapter 7. Chapter 7, as you can tell, deals specifically referring to the periodic table and some of the patterns and trends that we see on the periodic table. We're first going to talk a little bit about how the periodic table was developed. We're going to talk more importantly about effective nuclear charge, and we're going to talk a little bit about the sizes of atoms and ions. Okay, really the only thing you need to know about the periodic table is that the periodic table was first created by a Russian scientist by the name of Mendeleev. He is credited as creating the first periodic table. If you see here, it's actually very similar to today's periodic table. You can see here, for example, hydrogen, lithium, sodium, potassium, all in the same group there. Here you've got beryllium, magnesium, cadmium. There are certainly some blanks, some things that hadn't been discovered yet, but it's amazing how similar his periodic table is to our current periodic table today. And we can see that there's a lot of similar chemical and physical properties in these elements when they're in order of increasing atomic weight. Okay. Now, an important thing about the way that the periodic table is organized deals with what's called the effective nuclear charge. And if you think about those three words, the charge is obviously whether it's plus or minus. Nuclear just refers to the nucleus. And the effective means after you balance out all of the positives and the negatives, what is the actual charge that the electrons feel? So when we talk about the effective nuclear charge, that's referring to the charge that the nucleus produces that the electrons actually feel. So along with electron configurations, we also have to understand how strongly an electron is attracted to the nucleus to understand these the properties of different atoms. And there's basically three different things that affect how strongly an electron is attracted to the nucleus. One of them is the magnitude of the net nuclear charge. And basically what that means is the number of protons. The number of protons increases, then the strength of the attraction gets stronger. So the number of protons affects how strongly the electrons are attracted to the nucleus. Another thing is the distance between the nucleus and the electrons. The electrons that are closer to the nucleus are much more strongly attracted to the nucleus than the electrons that are farther away from the nucleus. So the farther away you get, the less attracted they are to the nucleus. And then number three, the number of electrons between the nucleus and the electron in question. This is the one that we're going to talk mostly about, is when you have, for example, the nucleus here, and then you have some electrons out here, and then you have an electron out here, and you want to know how strongly that one is attracted to the nucleus. These electrons here are blocking part of that attractive force. And so the number of electrons between the nucleus and the electron in question are what we're going to be referring to. Okay, now in an atom with a lot of electrons, each electron is attracted to the nucleus, again, depending on how close it is, how far away it is, how many protons are in the nucleus, and so forth. But at the same time, remember that although the electrons are attracted to the nucleus, they're also being repelled by the other electrons that are surrounding that atom. And so when we refer to the effective nuclear charge, which is written with a Z with an EFF, is equal to the number of protons in the nucleus, which is the atomic number, which is the letter Z, minus the number of electrons that are between the nucleus and the electron in question. Okay, many times these electrons here, the electrons that are in between the nucleus and the electron in question, those are referred to as core electrons or inner electrons, electrons that are in between the valence electrons and the nucleus. Okay, so mathematically we can write that as the effective nuclear charge is equal to the number of protons minus the number of core electrons. Okay, so we can see here that here we've got Z, so that's the protons. The yellow part here, that's the electron in question, and the orange part here in the middle, that would be the electrons between the nucleus and the outer electrons. Now, because these inner electrons are, again, these core electrons, because of those electrons, the outer electrons are shielded from the attractive force of the nucleus. Okay, a lot of times they also call them shielding electrons. So core electrons, inner electrons, shielding electrons, any of those terms are correct when you're talking about the number of number of electrons that are blocking the attractive force of the nucleus. So the effective nuclear charge experienced by the outer electron is determined primarily by the difference between the charge on the nucleus and the charge of the core electron. So the number of core electrons. Okay, so here, this got 12 protons, so this is a magnesium atom. A magnesium atom is 1s2, 2s2, 2p6, 3s2. And so we can see we've got our 12 protons in the middle, so that's our plus 12. And then all these right here are core electrons. So all 10 of these are the 1s2, 2s2, 2p6 electrons. And then these last two, these are the 3s electrons. These two electrons, the question may be, what is the effective nuclear charge experienced by these two electrons? Well, there's 12 positive charges, but there's 10 negative charges blocking those two negative charges out there. So overall, the combined effect is the effective nuclear charge of those valence electrons in magnesium is a positive 2. Because there's 12 protons attracting these electrons, but there's 10 electrons that are blocking these two electrons. Okay. Now, if we looked at, for example, instead of magnesium, if we looked at sodium, sodium would be very similar, but it would have 11 protons in the middle, and then it would still have the same number of core electrons. And so now you've got just this one electron out here. So in this case, for sodium, overall you would have an effective nuclear charge of just plus 1. Because again, 11 protons, 10 shielding or core electrons leaves you with an overall charge of plus 1. So that means that this electron that's out here, this electron here, experiences an attraction of plus 1, whereas the electrons in magnesium experience a charge of plus 2. And as you can hopefully see a pattern that as you go across the periodic table, the effective nuclear charge goes to plus 3, plus 4, plus 5. And as you go across, it just continues all the way up until you get to plus 7. Okay? And then when you jump down again, then the effective nuclear charge changes again. And we'll talk about that. So as I just said, as you move across the periodic table from left to right, so starting at sodium, going over to chlorine, or starting at potassium, going over to bromine, starting at lithium, going over to fluorine, you must be going from left to right. The effective nuclear charge increases. Okay? That's not what's that important. What's important is being able to explain why it increases. Because again, the number of protons in the nucleus increases. That's one important part. And the second important part is honestly, this part is not that important. The fact that the valence electrons increase is not that important. What is important is that the protons in the nucleus increases, but the number of core electrons remains the same. Okay, that's an important piece there, is that the reason that the effective nuclear charge increases is because as we go across the periodic table, the only thing that's increasing are the valence electrons. The core electrons are remaining the same, which means instead of, you've got 11 protons and then 12 and then 13 and then 14, so that the number of protons is increasing every time. What happens though is that the core electrons always stay the same. So you've still got 10 core electrons, 10 core electrons, 10 core electrons, all the way across the periodic table. Until you jump down, then the core electrons now increase. Okay? So the proton causes an increase in the attractive force of the nucleus. At the same time, the number of valence electrons increases. However, none of these valence electrons shield the other valence electrons. Only the core electrons shield the valence electrons. The core electrons are now shielding more valence electrons, which decreases their ability to shield. So again, if you've got the nucleus here and you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you've got this one valence electron out here, like on sodium, all 10 of these are very good at blocking this attractive force. Well, then once you get to magnesium, and you've got 2, now these 10 have to shield 2 electrons, not as effective. And then you go from magnesium to aluminum, and with aluminum you've now got 3 out here. This one, and this one. And so now, again, these same 10 are now trying to shield 3, not as effective. So the effective nuclear charge is increasing because of that as well. Now, how about as you go down? As you go from sodium to potassium to rubidium, or lithium up in there. As you go down a group, the effective nuclear charge increases, but only slightly. Okay, and this makes sense because the principal quantum number increases, which means the number of protons increase. But, as you know, as you go down, the number of core electrons is also increasing. So therefore, the effective nuclear charge doesn't change as much. The reason that it does increase slightly is because you add more electrons to it. Those shielding electrons that are shielding the valence electrons do not shield as well as in smaller atoms. So let's take that understanding and relate it to sizes of an atom. Because you would think that as you go across, that as you go from sodium over to chlorine, you would think, okay, well, the number of protons increases, the number of electrons increases, it's going to get bigger. And you'd also think, well, as you go from sodium down to potassium, that it's also going to get bigger. You're adding more protons, you're adding more electrons, blah, blah, blah. One of those assumptions is correct. The other one is not. Okay, the first one, number 1, deals with this right here. Within each vertical column, so as you go sodium, potassium, rubidium, lithium, within each vertical column, the atomic radius increases as you go down. So as you go from top to bottom, the atom gets bigger. Atomic radius, again, is just referring to the size of the atom. Why is a potassium atom bigger than a sodium atom? Okay, because as you go down the periodic table, the principal quantum number increases, which increases the number of electron shells. It's kind of like adding another planet to the solar system. When you add another planet to the solar system, you're obviously that planet, the solar system's orbit is going to get bigger. So if you just had Mercury, Venus, and Earth, that wouldn't be that big. But then when you add Jupiter to it, it obviously is going to get bigger. So when you increase the principal quantum number, you're increasing the number of electron shells, which therefore increases the size of the atom. Okay, that one does make sense. But as you go across the periodic table, this is the one you kind of have to think about a little bit. Because within each horizontal row, as you go from left to right, the size of the atom decreases. The size of the atom decreases because, think about again, effective nuclear charge. As you go from left to right, the number of protons is increasing. As the number of protons increase, the attraction to the nucleus also increases. Okay, so one of the parts is, again, the radius gets smaller, so the atoms get smaller as you go from left to right because there's an increase in the protons, which produces a stronger pull. Okay, so you've got this stronger pull from the protons, but then again, you have the same number of shielding electrons. So the two things you would want to mention on that is if they say on the exam, explain the following based on atomic structure, and they say a chlorine atom is smaller than a sodium atom, you would say that it's smaller because the number of protons that chlorine has is greater than sodium. However, they both have the same number of electrons, and so therefore chlorine experiences a greater effective nuclear charge, which makes the atom smaller. Okay, so here you can see it, that you start at lithium and go across. As you go across, they get smaller. Sodium across to chlorine, it gets smaller every time. As you go down, it gets bigger. Okay, again, it's not important in your ability to say, yes, I know nitrogen's smaller than carbon. Being able to explain why it's smaller than carbon is the important. Okay, so here we have one. Using just your periodic table, list the following atoms in order of increasing size. So we've got phosphorus, sulfur, arsenic, and selenium. So if we look at where they are on the periodic table, it goes phosphorus, sulfur, arsenic, and selenium. Okay, that's how they're organized on the periodic table. So in increasing size, so it means we're going to start with the smallest one. The smallest of them is certainly not going to be one of these two. We know these two are going to be bigger because they're down farther on the periodic table. Which one's going to be smaller though, phosphorus or sulfur? We know that sulfur is farther to the right. It has one more proton than phosphorus does. It has 16 protons. This one only has 15. But they both have 10 shielding electrons. So therefore we would say that sulfur is going to be smaller than phosphorus because it has more protons but the same number of core electrons. So sulfur is going to be the smallest, and then phosphorus. Then when we jump down, we know that these two are going to be bigger than the upper two, but we know selenium is going to be smaller, and then arsenic is going to be the smallest, or excuse me, the largest. So sulfur, and this is the measurement here. An A with a little 0 on top of it is called an angstrom. It's just a unit of measurement. It means 1 times 10 to the negative 10th meters. Not that important, but just if you see it, that's what it means. So sulfur is 1.02 angstroms, phosphorus is 1.1, selenium 1.17, arsenic 1.19. Okay, so here it is right here. Account for each of the following observations in terms of atomic theory and or quantum theory. Atomic size decreases from sodium to chlorine on the periodic table. So again, you would want to mention the fact that chlorine has more protons. However, they both have the same number of core electrons, which means chlorine has a greater effective nuclear charge. And again, you wouldn't necessarily have to include that. That's just one of those key words where if they see it, they go, okay, this person knows what they're talking about. Okay, so the way they describe it is, number one, they gave you 1 point for indicating the increase in the nuclear charge. So again, chlorine having more protons. And then you got another point is earned for attributing the size decrease due to the fact that greater attraction of the nucleus for the electrons caused by the increase in the nuclear charge. So across the periodic table, the number of electrons increases, as does the number of protons in the nucleus. The added electrons only partially shield the added protons, resulting in an increased, again, look at that, effective nuclear charge. This results in a greater attraction, drawing them closer to the nucleus, which makes the atom smaller. Again, would not have to include all of that. Just again, make sure you recognize the additional chlorine protons, and then noticing that they have the same number of core electrons, or a greater effective nuclear charge. Now, how about with an ion? With an ion, when you're dealing with an ion, remember that an ion is something that has a positive or a negative charge. So when an atom gains or loses electrons, its size will also change. So the size of an ion is determined by the distance between those ions in an ionic compound. So it depends on the nuclear charge, of course. Certainly it depends on the number of electrons gained or lost, and the orbitals that the valence electrons possess. Okay, now let's look at sodium. Sodium, again, 1s2, 2s2, 2p6, 3s1. You take that one electron away. So if you form a cation and you form Na+, it now is 1s2, 2s2, 2p6. So it's like we took a whole planet away. That one is now gone. That obviously is going to make the atom smaller. So when a cation is formed, when you have a positively charged ion, the atom gets smaller because you now have less electrons to attract, but the same number of protons. So the attractive force of the nucleus remains the same, which again, protons, the same. But it now has less electrons to attract, which makes that attraction stronger, which will make the atom smaller. And the opposite occurs with an anion. If you add electrons, so if you go from O, 1s2, 2s2, 2p4, to O2 minus, 1s2, 2s2, 2p6, again, same thing. Both of these have the same number of protons, but now there's 2 more electrons to attract in this one than in this one. So this one is going to be bigger because the protons are the same, but the number of electrons is now more. Okay? If 2 ions have the same charge, so let's say Mg2 plus and Ca2 plus, the size increases as you go down. Okay, so it's almost as if the charges don't even matter here. We know that calcium is so much bigger than magnesium because it's farther down on the periodic table, that the fact that they both have the same charge kind of cancels each other out, so we still know that calcium is going to be bigger. Okay, so here's just an example here. The gray is the normal size, so here's oxygen normally, and here's oxygen when it gains 2 electrons. It gets much, much bigger. Here's sodium normally. Here's sodium after it loses its electron. It gets much, much smaller. So you can see the big difference. Here's aluminum normally. When aluminum loses 3 electrons, it gets tiny. So when you have a positive charge, they get smaller. The pink is the smaller one. When they gain electrons, they get bigger. So the blue one is the bigger one. And again, the important part is being able to explain how and why. So using just periodic table, arrange these atoms and ions in order of decreasing size. So start with the biggest to the smallest. So we've got magnesium, and if you're not sure, write out the protons and the electrons. Magnesium's got 12 protons and 10 electrons. Calcium's got 20 protons, and with the 2 plus, 18 electrons. And calcium atom, 20 protons, 20 electrons. Now we know right away this is going to be the smallest. Okay, it's farther up on the periodic table. Calcium is farther down, so the smallest one is definitely going to be Mg2 plus. Okay, so without even looking at charges, we know that magnesium is going to be smaller than calcium. Okay, then between calcium, we know that calcium 2 plus is going to be smaller than regular calcium because it has less electrons to attract. So the biggest one is going to be calcium, and then calcium 2 plus, and then magnesium 2 plus. Okay, just about done here. If 2 atoms possess the same amount of electrons, they are said to be isoelectronic. For example, O2 minus and neon, you can't have like oxygen and fluorine. They're never going to have the same number of electrons. To have the same number of electrons, one of them is going to have to be charged, or both of them will be charged. For example, in this case, oxygen 2 minus, 10 electrons. Aluminum 3 plus, 10 electrons. Those two are isoelectronic in that they have the same number of electrons. Okay, oxygen normally has 8, it gains 2, it has 10. Aluminum has 13, it loses 3, it now has 10. So when they ask about things whether they're isoelectronic or not, it's whether they have the same number of electrons or not. Okay, and certainly in this case, you've got oxygen with 8 protons and 10 electrons, and aluminum with 13 protons and 10 electrons. Which one do you think is going to be smaller? Well, with the same number of electrons, the one with more protons, the attraction is so much stronger in aluminum than in oxygen because it's got 5 more protons than oxygen does. If we go back and look at that on that map, here we have aluminum. Aluminum with a 3 plus charge is 0.51 angstroms. Oxygen with the same number of electrons is 1.4 angstroms, almost 3 times bigger. So we can see that depending on what happens in that atom, whether it's got 8 protons or 13 protons, makes a huge difference with respect to the size of the atom. Okay, so here's that same question again that we saw the other day. They asked us, first of all, the previous question was something relating to part 1. You can see this is only part 2. Part 1 was draw the electron configuration for both these. So sulfur would be 1s2, 2s2, 2p6, 3s2, 3p4, and then s2 minus would be 1s2, 2s2, 2p6, 3s2, 3p6. And then part 2 asked you explain why the radius of the s2 minus ion is larger than the radius of the s atom. Okay, and hopefully you would recognize the fact that they both have the same number of protons. So same number of protons. However, s2 minus has 2 more electrons to attract. The more electrons there are to attract, the weaker the attraction becomes, making the atom therefore bigger. Okay, and then part B, we haven't actually talked about B yet, so don't worry about B. We're actually going to talk about that tomorrow. So maybe remind me tomorrow to come back to this question as to easier to remove an electron from. Okay, so let's look at the answer to part A again. Don't worry about B yet. The nuclear charge is the same for both species, so again, same number of protons. But the 8 valence electrons in the sulfide ion, so again, it has more electrons. experience a greater amount of electron-electron repulsion than the 6 valence electrons in the neutral sulfur atom. This extra repulsion of the sulfide ions increases the average distance between the valence electrons. So instead of having 6 out here, it's now got 8 out here, which again spreads them apart even more. So it spreads them apart, which is going to make that cloud even bigger. Okay, so that's your homework for tonight. This is a very important section. There's usually one free response question about this every year about sizes of atoms, and certainly some free response questions as well.